Okay, so we're gonna look at that first type of projectile motion today, but I'm just quickly gonna review where we've been so far with this. Last class we started talking about projectiles, and we talked about the fact that projectiles are two-dimensional motion. So motion in the vertical, so in the Y, but also motion in the X. So we're going to be looking at free fall in the Y. If you can do free fall problems, you've got this. And we're going to do URM problems in the X. So if you can calculate velocity, you're okay with this. So first things first, we're going to look at projectiles launched horizontally. When we actually started talking about this, so this is just what I just said, we launched a marble at the same time as we dropped a marble. All that to prove that things fall to the ground at the same time because there is no acceleration in the X. Okay, we talked about the independence of both axes. We tried to prove this. We were pretty darn close. And then now we're going to actually get into projectiles launched horizontally. So no actual angle of elevation or angle of depression. Okay, so these were all the variables we talked about. We talked about how because in the X there's no acceleration, you have way less variables to deal with. This is why it's URM. Whereas in the Y, these are going to be just like free fall problems. We looked at our equations and we looked at what happens when you remove acceleration from the equation. Essentially, we're left with these two equations right here, which if you actually think about it, these guys are nothing more than this being rearranged and expanded upon. Okay? You know that your UARM equations in the Y, so these guys way over here, these guys aren't changing. These are the same things that we learned about in the last unit. Excuse me. Now, let's look at what our graphical expectations are when we talk about this stuff. So we're going to look at our X again, X over T, our V over T, and our A over T, right? And this guy here, these guys here are going to be in the X axis, right? These guys down here are going to be in the Y axis. So we're also going to look at our X over T, our V over T, and our A over T. In the X, you guessed it, it's URM. Therefore, we have no acceleration. That implies that our motion, all right, is going to be at a constant velocity. That velocity is going to go straight up and there's going to be no acceleration. Okay, we've done this before. Same thing happens if you're starting from up top and something is dropped to the ground, right? Your position is going to change. Okay? What happens in the Y though? In the Y, we see the exact same thing. It's going to start from up top and it's going to slowly fall to the ground. Okay? So we see that the position is starting from up top and it can be the exact same thing here. We can change this up where we're just going to see some accelerated motion, right? So change in position over change in time. If we want it to be really legit and something was dropping from the ground, it would actually have, let me just get this going here. Sorry about that. I'm going to erase this and just add in if we're dropping something, right, from a height and it's falling to the ground, it's going to do something like this, which means that over time, right, its velocity is going to start at 0, and its velocity will start to get faster and faster and faster down here, which means it's going to have a negative acceleration, right? So we've looked at this before. None of this should be new. The reason I drew this way as opposed to going up like so, and like so, is that the acceleration, the UARM and the Y, is actually free fall. So it's going to start from a height and it's going to be launched. And that means it's just going to move forward and fall to the ground. It's not going to go up at all. It's just going to go straight and start to fall. All right, so projectiles launched horizontally. So when I just said it's going to go straight and start to fall, this is exactly what I meant. You'll notice here in the trajectory of this little skateboarder dude, there is 0 angle of elevation or angle of depression. There is no angle of launch here, all right? So when we're talking about things being launched horizontally, there's some things that are implied there. When something is launched horizontally, if you look at that image, the only vertical thing that this thing can do, this object can do, is it can fall to the ground. It's not going to go up because there's no angle of elevation. Okay, so that tells us something. Automatically, when you know that you have a projectile launched horizontally over here, okay, automatically you know that your VIY is going to be 0 because this is the same as free fall, right? It's almost like dropping something from a height. It's exactly as you did in your lab, and it's exactly what we did with our marbles when we made that little video. You know that your we're not going to actually talk, and this is actually not correct. There's an error here, so I'm going to change this. Your actually no, there's no error because I didn't even notice. Your VIX is going to be greater than 0. It needs to have an actual velocity in the X because that is what's going to launch it forward. And if your VIX is greater than 0, and this is URM, you see that these two here are going to be the same, VFX and VIX. Your velocity in the X does not change. Okay? So, when you look at acceleration, there's no acceleration in the X. You always know your acceleration in the Y. It does not change. Your VIY, because you're dropping it essentially from rest, will be 0. Your VFY, its magnitude will be greater than 0, but its direction will always be negative. Because if you look at this, right, remember our arrows from way back when, we're starting here and the arrows are getting bigger and bigger and bigger and bigger, okay? So that means the velocity is getting greater and greater and greater and greater, okay? And the actual way we could draw that, to really be honest, would be kind of like the invert of this. So if this was your x-axis here, right, you would see that it starts off at 0 and it gets bigger and bigger and bigger. That means the magnitude of the velocity in the y is increasing. Okay? So when we look at this, let's look at an actual problem here. From the roof of a building that is 50 meters high, a ball is thrown horizontally with a velocity of 5 meters per second. What is the ball's position at t equals 1 second, t equals 2 seconds, and t equals 3 seconds? So these are three tiny little calculations, right? So we're looking for a few things here. I'm going to start off by writing out my givens. So my givens, I've got some stuff here. All right, so my givens. I know that my building is 50 meters high. I know that it is thrown horizontally. I know that I have a VI here, right? I want to know what the ball's position is, okay? And I've been given time. I've been given time at 1, time at 2, time at 3. What is wrong with this question, though? What is wrong here? There is a problem with this question. There's a problem with the wording. And yes, this question is right out of your textbook, but there's a problem with its wording. You have 2 potential positions to find, not 1. Okay? This question should have been more specific with the X position or the Y position, because if you are launching something from a 50-meter high building, it is going to drop. Its YI is 50. At some point, its YF will be 0 when it hits the ground. At the same time, because it's being thrown horizontally, its XI will be 0, but its X at 1 second, at 2 seconds, and at 3 seconds will be different. Okay? So that's my issue with this question. Let's assume that we're going to go with the actual Y. Okay? Let's look at the Y position. So if I write my givens, I know that YI is going to be at 50 meters. I know that my VIY is 0 because it's launched horizontally. I know that my VX is going to be 5 meters per second, right? I know my VFX too. I know my acceleration in the Y, going to be negative 9.8 meters per second squared. I know that my time, so we're going to break this down. We're going to go with TF equals 1 second. So that's TF1. TF2 is equal to 2 seconds. And TF3, 3 seconds. Because these are 3 different calculations, okay? But you're essentially going to do them the same way. If you look at these variables, do you have a VFY? Right? VFY, we don't know. It's going to have a VFY because its VIY is 0. So if that's the case, if you do not have a VFY, then automatically you've got one equation that you can use in the Y, and that is equation number 3. It is the only one that does not have VF in it. Okay, so in this case, X final is equal to, or Y final, sorry, might as well get used to writing the right ones. Y final is equal to Y initial plus VIYT plus 1/2 AYT squared. So automatically, let's cancel what we can cancel, please. We know that the position in this case is not going to be 0 because it probably will not have fallen to the ground yet. But I know my VIY is 0, so this whole thing goes to 0. All right, and I'm left with YF is equal to 50 meters plus negative 9.8 meters per second squared times 1 second squared. All that is divided by 2 over here. I don't have any rearranging to do, because it ends up, I'm looking for what I've got here. So if I was smart, I would have already had this done, but I didn't think of it. So I'm going to punch it in on my calculator right now. So if I've got 9.8, right, divided by 2, and 1 squared is 1, and I'm going to add this to 50 meters. At t equals 1 second, my y final, okay, so my first y final is going to be 45.1 meters. You can do the second, the third, and the fourth, right? Once you have this, though, you could also determine the actual x position. So if we were determining the x position, the same rules would apply, except, holy moly, the formula changes drastically, right? Because your xi is equal to 0 meters. You don't know your xf. You've got your t, that's 1 second. And you've got your v, right? Your vx is 5 meters per second. So it's good old-fashioned v is equal to delta x over delta t. You're just rearranging here. X is going to give you, and by x I mean x final, because x initial is 0, is going to be vx times t, which is equal to 5 meters per second times 1 second. So that's going to be 5 meters. If you take a second and just logic this out, you can probably determine what the change in x is going to be for every one of these, right? Because it's URM. If in the first second he moved 5 meters per second, in the second he will have moved 10. In the third second, he will have moved 15. Okay? Now, if we look at this, now we start to have some fun. And we start to see some of the x and y components play into one another. Okay? Case in point, if we go back to this equation here, this sheet, and it had our list of variables, we see that there's one variable that it doesn't matter whether you're in the x or the y, it stays the same. That is time, because time is a scalar quantity. You could solve for time in the x or in the y, it will still be the same answer. So when you look at a question or a slide like this, and it says, oh, A, B, and C, well, in this case, you may have to use the y to solve for time, okay? You may have to then apply it, right, to another question once you've solved it. And if I look at these questions, the first one is exactly that. It's asking you to solve for time. How long does the ball drop? How long does that take? Once you get that time, you have your Vx, then you can figure out your x, and then you're going to find your Vyf. Okay? And that's all vectors. All right? So if we look at this, solving for time for A, so my givens here, I'm just going to write them up here. My givens, right? I know that I've got a yi of 50 meters. I know that I've got a Vx of 5 meters per second because it's launched horizontally. I know that my AY is going to be negative 9.8 meters per second. All right, and you know all the other things that are zero. My my VIY is 0 because this is launched horizontally, right? VIY equals 0 meters per second. I don't know my VFY. It's actually asking me to calculate it later. So for A, for time, again, I'm gonna have to use, all right, I am gonna have to use probably my third equation, because we do not have the VF. So if I look at this, and I cannot solve for time in the actual X because I don't have position either. So in this case, if I write this out, YF is equal to YI plus VIYT plus 1/2 AYT squared. Now, this is a quadratic. We do not have to do a quadratic here though, but quadratics will be a part of projectiles launched at an angle. I'm telling you that right now. Okay? In this case, no quadratic because our VIY is 0. So see you later, sucker. And we're just left with rearranging this for t squared, right? So we end up having something like 2 negative yi, because I'm bringing this guy over here. I bring this guy over because I don't need him. This guy's 0 because it's going to fall on the ground. Okay, so just going to change this up here. And you're going to see that it ends up working out. We've got negative 2yi because I brought it over. And that is going to be divided by ay, which is going to be equal to t squared. Take the square root of both of those, you're going to get your t. So work this out. Don't have my calculator ready here. What do I got? You can probably figure this out before I actually get my calculator out. There we go. Okay, so we end up with negative 2 times 50 meters, and that is over negative 9.8 meters per second squared. And this is interesting, right? If you sit here and you look at the units, that is going to cause the s squared to be bumped up to the top because it's the denominator within the denominator, right? And you look at this, and that is equal to t squared. So if we're looking for time and we square root both of these, we're going to be left with seconds. So the units act as a proof. All right, so if I sit here and I do 2 times 50 divided by 9.8, and then I take the square root of that, right? What am I ending up with here? Oh, I don't think I pressed something right. Anyway, you can figure it out. T is going to be equal to a number, right? Once you have that T, using the Y values, you can then go in and use T to solve for the change in position. Because if you draw this out, what's happening here, right, is you have your 50-meter tall building. So this is 50 meters, and this projectile is being launched like so. So it wants to know the position. This is B, right? A was time. B is the position change in the X. And C is going to be the rate at which it's falling right before it hits the ground. So for B, that is going to be nothing more than X final is equal to Vx times T that you just calculated. Then we can go back for C and we're going to have to find Vf because it wants to know the magnitude of the ball's velocity the moment that it touches the ground, right? And what is its direction. So in this case, you've got three choices. Personally, you could go with A, you could go with B, you can go with equation 1, I would ignore equation 2, but that's just me because it's a lot more rearranging. Equation 1 or equation 4, easy peasy. Okay, so you can use equation 1 or equation 4 to solve it, and there is your answer. So VFY is going to either be equal to VIY plus AYT, or VFY squared is going to be equal to VIY squared plus 2AY delta Y. Right? And you know that this guy here is 0. You know that this guy here is 0. That's how you go about solving these problems. So for the rest of the period, I want you to work on projectiles launched horizontally. And then next class, we will do projectiles launched at an angle.